So welcome everyone. A reminder, feel free, please keep muted during the talk, but feel free to unmute yourself if you have questions during the talk. You can also put questions in the chat, whichever you prefer. It's a pleasure to welcome Fernando Galaz-García from Durham University, who will speak on geometry and topology of collapsed three-dimensional Alexandrov spaces.
Thank you very much, Caroline, and thank you also to Ramiro and to Emilio for the invitation. It's a pleasure to give a talk in this seminar, and thank you everyone for joining. I have given this talk before in other seminars, but so I tried to add something slightly slightly more detailed towards the end. So, but you know, feel free to tune out at some parts if you have already seen this. And so let's start. So first of all, I want to just mention that this talk is on joint work that I've done with Luis Guijarro, who is at Universidad Autónoma de Madrid in Spain, and with Jesús Núñez-Zimbrón, who is now at CIMAT in Mexico. So this started originally with a project with Luis Guijarro, where we wanted to understand the topology of Alexandrov spaces in dimension 3. So actually the original question was, is there something like the Poincare conjecture for these spaces? And then this made us think about the topology, and so I will discuss that, and then an application of all this work to collapse of spaces in which actions play a role. So as maybe not everyone is familiar with Alexandrov spaces, let me start with a very, very general question. So, I mean, this question is a theme in geometry. So, well, you want to understand how the geometry influences the topology of a space. Right, so this is the theme of global Riemannian geometry. And one can think of Riemannian geometry as sort of being a special case of Alexandrov geometry, at least in the case where you have sectional curvature bounded below. Right. So then Riemannian geometry deals with smooth Riemannian metrics and smooth manifolds, and then Alexandrov geometry is sort of a non-smooth generalization to metric spaces in which a lower sectional curvature bound holds. So the sort of going back, well, we want to work with a special kind of metric spaces called length spaces, and so let's just define them. So a length space is a path-connected metric space, x with a distance function, and what's special is that the distance is given by the infimum of lengths of curves joining 2 points. So if you have 2 points P and Q, then you look at all the curves or the paths joining them, and these paths gamma are in a special collection of curves that I call omega PQ, which are rectifiable. So these are curves for which the length makes sense, it's finite, and then you look at the infimum. So this is, in the Riemannian case, this is how you define the Riemannian distance, by looking at the infimum of lengths of piecewise smooth curves joining 2 points. So then how do you define here the length, right? So this is an idea. So you take a curve, and then you start taking a partition of the interval in which it is defined, and then you look at points, and then you start looking at the distances between consecutive points. So here, this is a picture in the Euclidean plane, right? So here, the distance between 2 points it's just the length of this straight, and then you start taking finer and finer partitions, and then you take the supremum of all these sums of these straight lengths of these straight lines, and that gives you the length. So these are length spaces. So we will work with length spaces, and so now we have special type of curves which are called geodesics. So a curve is a geodesic if its length is a distance between its endpoints. So here, geodesic, well, you can think of it as it's really the shortest curve or shortest geodesic. So for us, the geodesic will always be the shortest curve. So this is slightly different from the term in Riemannian geometry, right, where so you can have geodesics, but they're not globally minimizing. So here, every geodesic minimizes the distance. And then, well, we want to work with special type of length spaces. So they're called geodesic spaces. And these are spaces in which any 2 points can be joined by a geodesic. So throughout the talk, you can just keep in mind Riemannian manifolds, complete Riemannian manifolds are length spaces, and they're also geodesic spaces. So in a complete Riemannian manifold, you can always join any 2 points by a shortest geodesic. So the idea now is to try to make sense of curvature. So for Riemannian manifolds, we have different notions of curvature, but the one that generalizes the Gaussian curvature is sectional curvature, and we want to try to make sense of such sectional curvature for metric space or for geodesic spaces. And the idea is to use triangle comparison, and you want to compare triangles in length in geodesic space with triangles on model space, which one understands well. And these model spaces are two-dimensional, simply connected Riemannian manifolds with constant curvature k. So I will denote them by S2k, and so let me use here this spotlight. So these are S2k is a surface. It's complete, simply connected with constant curvature k. So this is a round two sphere. If k is positive, it's a Euclidean plane if k is 0, and it's hyperbolic space if k is negative. Okay, so here we have a sphere, a round sphere, and here a piece of Euclidean space, and here this is the model for hyperbolic plane. And well, so here you can see some triangles, right? This is a Euclidean triangle. Here, if you take, for example, this North Pole and 2 points on the equator, you have some triangle here, which, I mean, just observing, it's in some sense fatter than the triangles in Euclidean space. And here you have these geodesic triangles are sort of thinner. So well, I guess we always hear that triangles are related to curvature, and we want to make some formal sense of that. So let's continue. So okay, so now, well, so what is a triangle in a geodesic space? So you take 3 points and PQR, and then you take 3 geodesics, so 3 shortest curves joining them. So this is a geodesic joining P and Q, and this is PR, and a geodesic joining QR. Now you have this triangle in the geodesic space, and then you want to compare it with a triangle in the model space with constant curvature k. So then for that, you have something called a comparison triangle, which is a triangle. This is with PQR bar. So this bar denotes triangles here in the model space. And what you want is that the sides have the same length as the sides of this triangle. So let me see if I can draw now. So let's see here. Right, so if you have, for example, a triangle here, let's draw this. I'm using this tablet here, so let me see some. Right, so here you have, say, P, Q, and R, and then this would be, for example, S2K, and this is in X, and you want the sides to have the same length. So these corresponding sides have the same length. So this would be P bar, U bar, and R bar. Okay, so let's continue. So okay, so now we want to define a curvature or a lower curvature bound, and this is captured or sort of by this property tk for 3 points. So k you can think of it as for t for triangle or for Topologov. So the idea is the following. So I'll draw a picture. So here you have a geodesic triangle in your geodesic space. You have 3 points and the sides, and then you have a comparison triangle in the model space. So you have P bar, Q bar, R bar, and now. Right, so this is a comparison triangle. So this is just a picture that I drew before. And you want to take now a point here, S, on this side. So you look at the side QR and you take the point S here. And now remember, this is a the triangle here has this is its corresponding comparison triangle. So these two sides, QR and Q bar, R bar, have the same length. So this point has a corresponding point S bar on this side that is at the same distance from Q bar as S is from Q. Okay, and because these sides have the same length, this implies that S bar is at the same distance from R bar as S is from R. And now what you want to look at is the distance from P to S, and you want to compare it with the distance from P bar to S bar. So here I'm drawing. So suppose this is a shortest curve, a geodesic. So the distance is the length of this curve. And then you look at this distance. And then what this property says is that, well, or this property holds if this distance from P to S is greater than or equal the distance from P bar to S bar. So for any point on this side. So this is just in words. So if you take a triangle in the space, in the geodesic space, then you take a comparison triangle. Then the property holds if for any point here, S, right, in this geodesic from Q to R, the distance from P to S is greater than or equal this distance between P bar and S bar. So this, I mean, you can keep this picture in mind, right? So this says that, well, this is at least as curved as this space. And now, so an Alexandrov space with curvature bounded below is a complete geodesic space with finite Hausdorff dimension, where this property Tk holds locally. Let me just go back. So here, so you may ask, well, where does this come from? Why are we taking this as a notion of a lower sectional curvature bound? So this is actually a theorem for Riemannian manifolds with lower sectional curvature bound K. So if you have a complete Riemannian manifold with sectional curvature bounded below by K, then this property holds, and that's Toponogov's theorem. So this is, you can think of this as a metric sort of it's a metric way of saying that you have sectional curvature bounded below by K. So then this only involves distances. So then you can take it as a definition for a geodesic space. So then this is what an Alexandrov space with curvature bounded below by K is. So, and so again, you can think of a complete Riemannian manifold with a curvature bounded below by K. Those are Alexandrov spaces. So this is, for example, these are examples and of Alexandrov spaces are boundaries of convex bodies in R3. So for example, this tetrahedron is an Alexandrov space. So if you look at it, if you try to do this property Tk, this will satisfy T0. So this has curvature greater than or equal 0. So for example, on these sides, basically this is flat, except at these at its vertices. So, but here the inequality holds. So, and well, this is homeomorphic to the two sphere, but it's not smooth, right? So the metric is not smooth at this. So now this is a non-example. So this is a graph, right? A tree. So the problem here is that if you take what does a triangle look like? So it's going to look like a T, right? And then if you want to find a comparison triangle, you need to let K go to -infinity. So you can think of this as not having a lower curvature bound around these points where three geodesics meet. So this is an example, on the other hand, of a cat zero space. So one can switch the inequality here, and that would mean that you have curvature bounded above by K, but we are not going to talk about those. So for example, something that happens here that we do not like, well, at least in this talk, maybe you like it, in general, is that geodesics branch, right? So you can come here with a geodesic and then you can continue in two different ways. But we know that this does not happen for Riemannian manifolds. So, and actually one can show that geodesics do not branch for Alexandrov spaces, and that the, well, there's also this globalization theorem of Topologov. So this property Tk holds globally. So not only locally, that's in the definition, but it holds for any geodesic triangle in the space. And also the Hausdorff dimension of the space is an integer, and it's constant. So for example, for these cat zero spaces, you may have sort of the dimension may not be constant, and so sort of what you can think of these comments as saying that, well, topologically they're not too bad, right? So in particular, for example, there are no things like fractals, right? That where you have non-integer Hausdorff dimension. So so then you can ask, well, in that sense they are well behaved, although, well, I guess when I first started thinking of them, I thought they were very bad, but then you learn there are other things that are much worse. So so then one can hope to give some, well, try to really understand the topology. So this talk is going in that direction. So let's just give some examples and constructions. So so as I said, complete Riemannian manifolds with a lower sectional curvature bound are K, are Alexandrov spaces. That's Toponogov's theorem. Boundaries of convex bodies in Rn are also Alexandrov spaces. So here we have another sort of convex boundary of a convex body. So this is a dodecahedron, and that's also homeomorphic to S2. One can also put together spaces by taking cones and suspensions of Alexandrov spaces with curvature bounded below by 1. So this is very special if you compare it to the manifold case, in which finding examples of manifolds with positive curvature is very difficult. Here you can take cones, right? And suspension. So what this means is that if you take a cone or you take a suspension, that's a topological procedure, then you can find a metric such that the space has curvature bounded below by 1 if your original space had curvature bounded below by 1. So this is just a sketch of a suspension. So you can think of this as being the space with positive curvature. And then this is the suspension topologically is like taking two cones and you join them, so you glue them, and then you get this. For example, this sphere is the suspension of its equator. Now, more generally, one can glue spaces. So you can take two Alexandrov spaces with isometric boundaries. And then if you have assume that you have the same lower curvature bound, then you can glue the boundaries and get a new one with the same lower curvature bound. So this picture is called the double disk. So here, this is a disk in our Euclidean space. So this is a space with non-negative curvature, and then you take another copy, and then you just identify its boundaries, the boundary, and then so it's flat almost everywhere except at this where the identification is carried out. So, for example, this is topologically S2. This is another metrically is different from this one or from the round two sphere, but topologically it's S2. Right? So we're just going to flat disks together. One can also take quotients by groups of isometries. So here you take Y is a space with lower curvature bound K. Then you have a group G acting, assume it's compact, or more generally you need closed orbits. And then you can put a metric here, and this new space has the same lower curvature bound K. So this is sort of, if you think about it, this follows from the fact that the orbit projection map does not increase sort of distances. So, and now one can also put together new Alexandrov spaces out of certain pieces, right? If you have a certain compact stratified space, and these sort of manifold pieces have lower sectional curvature K, then, well, under certain cases, you can construct a metric on the stratified space. So out of all these constructions, this is actually fairly recent. So this was proven by Bertrand, Ketter, Mondeno, and Richard. And actually, this was proven for RCD spaces and then also for Alexandrov spaces. So, but the main drive of this paper was RCD spaces with generalized Ricci curvature. So, okay, so maybe are there any questions so far? Oh, okay, so well, maybe this is to convince you that you have a lot of spaces, and for example, many are not manifolds. You can also take, for example, suspension of complex projective spaces, and that gives you Alexandrov spaces, so they're not even orbifolds. So, and now this is relevant. This is the most relevant part to our talk today, is that they also arise as Gromov-Hausdorff limits of compact Riemannian manifolds with a lower curvature bound K. So the idea here is that if you think of the sort of, you look at compact metric spaces, there is a metric on that class of spaces called the Gromov-Hausdorff metric. So then you can make sense of convergence sequences, convergence. Basically, you put a topology on that space, and then what this says is that if your sequence of metric spaces consists of Riemannian manifolds of dimension n with a uniform lower curvature bound, then the limit is an Alexandrov space. With the same lower curvature bound as the elements of the sequence. So now here one can show that the dimension of the limit does not go up. It has to be at most n, but it can go down, and that is what is known as collapse. So before jumping into that, let me talk about the local structure. So so keeping in mind this sort of example or familiar example of Riemannian manifolds, well, so we can, on a Riemannian manifold, if you take a point, then you can look at its tangent space, and then you can take well, the tangent space is Rn, right? It has the Riemannian metric gives you an inner product, and then you can look at the unit tangent sphere, and there is a corresponding object for Alexandrov spaces. So it's called the space of directions. So one can define first angles between geodesics, and then this gives you a notion of a tangential direction. So in the Riemannian case, these are tangent vectors. And then one constructs a space called the space of directions of x at P. And again, for a Riemannian manifold, this is the unit tangent sphere. And the corresponding object for an Alexandrov space is the space of directions. And so then a basic theorem of Burago, Gromov, and Perelman says in the paper that laid the foundations for this theory, says that if you take the space of directions and then you put the angle on it, so this is the this gives you a metric space, and then this has curvature bounded below by 1. So for Riemannian manifolds, this is the round unit sphere, which actually has constant sectional curvature 1. So as an Alexandrov space, it has curvature bounded below by 1. And as in the case of Riemannian manifolds, the dimension of the space of directions is 1 less the dimension of the space. So just and now a very deep theorem of Perelman says that, well, that every point in an Alexandrov space has a neighborhood that is pointed homeomorphic to the cone over the space of directions. So the corresponding statement for Riemannian manifolds is, well, you learned that in a Riemannian geometry course, is that sort of on a small neighborhood of a point, the exponential map is a diffeomorphism. So that gives you, so Rn is a cone over the n-1 dimensional sphere. And then on a Riemannian manifold, the exponential map gives you a diffeomorphism of a small sort of ball onto a metric neighborhood. And now, well, this is very nice. This is the what you would like to have. But notice that here for Alexandrov spaces, we do not have the smooth metric. There's no exponential map. There's no smooth tools. So one has to prove this in a completely different way. So it's certainly not an immediate thing. And so there's really there are some deep results behind this. And so, but the upshot is that, well, it gives you the local structure of an Alexandrov space is then determined by the space of directions. And here I should probably mention that there's a conjecture, right, that this homeomorphism can be improved to by Lipschitz, right? So this is something that is Perelman said could be done, but there's no written proof yet. So and that's what's expected. That would be the complete statement. So now let's go back to this. Now going back to the Gromov-Hausdorff distance. So as I said, well, where do these spaces arise in Riemannian geometry? So you can look at the closure of the set of compact Riemannian manifolds here, M and KD. So with sectional curvature bounded below by K and diameter bounded above by D. And now, so then you take the closure under the Gromov-Hausdorff topology. So that is, you take limits of all these sequences in this space. And then elements in the closure are Alexandrov spaces with curvature bounded below by k, diameter bounded above by d, and dimension at most n. So, I mean, this is not to say that every Alexandrov space arises as a limit of a Riemannian manifold. So that's an open question. What this is saying is that any space in the closure is an Alexandrov space. So here, as I mentioned before, the dimension cannot go up, but it could go down. So let's look at what happens, right? If the limit here, the dimension is the same as the dimension of the elements in the sequence, then again, the theorem of Perelman's, the stability theorem, implies that if you have two compact n-dimensional Alexandrov spaces with the same lower curvature bound, if they are sufficiently Gromov-Hausdorff closed, then they are homeomorphic. So if you are interested in understanding the topology of the spaces, well, this tells you that if you have a Gromov-Hausdorff conversion right, of spaces with the same dimension, then the tail of the sequence is homeomorphic to the limit. So then if the sequence is non-collapse, meaning that the dimension of the limit is the same as the dimension of the elements of the sequence. So from that, so this answers this question of what does the topology of the limit look like? So now, well, the question that now you can ask is, well, what's happening if the dimension of the limit goes down? So that means that the sequence is collapsing. So just to get an idea or a concrete picture, you can think of a very simple picture of collapse. So intuitively is, well, you can think of the torus. So this is just as a manifold, but now I want to think of the flat torus. So just think of this really as the flat torus, where you identify this curve with this one, and this side is identified with this one. So this flat torus, right, it's S1 metrically is S1 cross S1. So this is a circle. So all these vertical slices are circles. And then you can think, well, you can start shrinking one of the factors. So this would correspond to shrinking one of the sides of this in this square. So this is what I'm showing or drawing here. And then sort of in the limit, well, you converge to this interval here. But remember here, this point is identified at this point, so we get a circle. So this is just this is saying that, well, the flat torus is collapsing to a circle, and in general, collapse is sort of related to having circle actions. So here on the torus, you have a circle action, right, where you can just act on one factor, and the orbit space is going to be a circle. So now we want to understand what's happening with the collapse of three-dimensional spaces. But before that, well, why 3 dimensions? Because, well, we're interested in topology, in the global topology of these spaces. But then in dimensions 1 and 2, there's not much to say. So if we take a closed Alexandrov space, here closed means compact and without boundary, just as for manifolds. Well, before I should tell you what the boundary is. So in the way you define the boundary is you do it inductively. So in low dimension, in dimension 1, an Alexandrov space is a topological manifold, or actually in dimension 1, it's just a circle or an interval topologically. So you know what the boundary is for that. And then you define the boundary of an Alexandrov space. So a point is in the boundary if its space of directions has boundary. Okay, so but here in dimensions 1 and 2, the topology is there's not much to say. So these are topological manifolds. And in dimension 3, this is where something new happens. So here in dimension 3, X space is homomorphic to either a 3 manifold or it's a quotient X tilde mod iota, where X tilde is a closed orientable smooth 3 manifold, and this map iota is an orientation reversing smooth involution with only isolated fixed points. So what this is saying is that if you take a 3-dimensional Alexandrov space, then, well, it's either a 3 manifold, then you're in 3 manifold topology, or you can always, there is always a 3 manifold that's orientable with an involution, and then when you take the quotient, you get the non-manifold space that you had. And what's important, well, a key thing here is that this involution is orientation reversing, and it only has isolated fixed points. So just to fix or get a concrete example, we can look at a specific involution. So here I wanted to make this comment because so it turns out that these topological spaces, that these they had sort of come up before in topology. So they were called singular 3 manifolds, and they're exactly the underlying topological spaces of the Alexandrov spaces, which are not manifolds. So they called them singular 3 manifolds, and then there were some things proven, but yeah, there wasn't so much work done on that. So this was they were introduced by Quinn in 1981. So you can say that the underlying topological space of a non-manifold Alexandrov space is a singular 3 manifold in this sense of Quinn. So what is an example? So a very concrete example that it's the simplest, well, probably the simplest example you can think of a non-manifold Alexandrov space in dimension 3 is the following. So you take S2, the round S2, you take the antipodal map. So you take this point, you map it to this point, and then you take its quotient, you get here the real projective space. This is the round projective space here. And now I want to draw something in dimension 3, so I will think of this as being one-dimensional. This is S2, and RP2 is just a shorter circle. And now we take the round 3 sphere is the suspension of S2 with this spherical suspension metric. And now I can take the suspension of the antipodal map acting on each sort of slice here. And then the quotient is going to be the suspension of RP2, the spherical suspension of RP2. And now if you forget about the metric, and you just look at the suspension of RP2, these 2 points here have neighborhoods which are homeomorphic to cones over RP2, okay? And then, so you can think of sort of chopping off these. So these things are cones over RP2, and then you can think of just chopping them off. You take off these cone points, and then what you get is this knot. I call it this sort of the manifold part. So this is RP2 cross 0, 1. And then conversely, right, if you start with RP2 cross 0, 1, you can, it would be this part. You can glue in these cones, and then you obtain the suspension of RP2. So this is another way of thinking, is you take a 3 manifold with finitely many RP2 boundary components, and then you glue in cones over RP2, and that's the general structure of a non-manifold Alexandrov space. in dimension 3. Okay, so now let's the theorem, just to state the theorem, I just need to remind you what a little bit of three manifold geometry. So let's just recall that a model geometry is a simply connected smooth manifold with a transitive action of a Lie group that has compact stabilizers. So these are homogeneous spaces. And then among such geometries, there's, well, one is maximal if this group that's acting is maximal. And then Thurston, so he showed that there are 8 maximal model geometries that have a free co-compact isometric action of a discrete group, gamma. Okay, so the co-compact just means that the quotient is compact, and then the action is free, so you get a manifold. And these are the 8 geometries. So you have S3, R3, hyperbolic geometry, and you have these product geometries. And then you have these 3 universal color of SO2R, neo, and so. So it's not really important, the purpose of the talk, that you know what these are. It's just important to know that there are 8. And if, well, and then there's the geometrization conjecture, or the statement that you can sort of build all closed free manifolds from out of these geometric pieces. And manifolds that can be obtained as quotients of these 8 geometries are called geometric. So now for an Alexandrov space, we can also define, well, this immediately what is an Alexandrov space. What a geometric Alexandrov space is by just saying, well, it's homeomorphic to a quotient of one of these 3-dimensional geometries by some co-compact lattice. So now here we're no longer asking that the action be free. So you could have either metric or topological singularities. And now here, this is sort of the start of the story, was this paper with Guijarro, where we classified spaces with positive or non-negative curvature. And then one can also show that every Alexandrov space has a geometric decomposition, as is the case for topological manifolds. So, but now the theorem I want to present to you today, or the goal where we're going, is about collapse. So we want to understand the, well, if we can say anything about the topology of collapsed 3-dimensional spaces. So this is a more formal definition of collapse, right? So as I said, so if a space is collapsed, if you can find a sequence of metrics on this space of Alexandrov metrics and a limit space, and you want all to have the same lower curvature bound such that the Gromov-Hauser limit of this sequence, right? So this is going to be a sequence of Alexandrov spaces, is this space Y. And here, this is the collapse part, is that the dimension is strictly less than the dimension of the sequence. So now Shioya and Yamaguchi studied the topology of closed collapse Riemannian manifolds. This is in 2000. So in particular, you can cross this off and put Riemannian manifold here. So, and this turned out to be useful in the proof of geometrization. And but then you can ask, well, what can we say if we just look at Alexandrov spaces instead of Riemannian manifolds? So more recently, Mitsubishi and Yamaguchi, they studied the topology of closed collapse 3-dimensional Alexandrov spaces. And they can be described as a union of certain pieces. So, but the pieces can be complicated. So, for example, one can get something called generalized Seifert spaces. And these are pieces with topological singularities. So these are, for example, they have these points where a neighborhood of that point looks as a cone over RP2. On the other hand, they are not so bad, one can describe them as a union of, so a Seifert space, if it's a manifold, you think of it as it's a space which can be decomposed into fibers, which are circles. And here, this generalized hyperspace is a space in which you can decompose it into fibers, which are circles, but you also have some fibers that are intervals. And then you put all these together, and then you can get these generalized hyperspaces. And those are an example of three-dimensional Alexandrov spaces that collapse. So they sort of looked at the local structure, and they have actually sort of topological, quite complete topological information on these spaces that collapse, for example, to dimension 0, 1, or 2. So those are our possibilities. And the theorem that we proved, sort of putting all of these things that I have talked to together, is this result of Jesús. So this says that if you have a space that is sufficiently collapsed, then it's actually geometric. So you have a positive constant d, going to be up and right, and you can find an epsilon such that if X is a closed irreducible Alexandrov space of kind, this is just to normalize the curvature bound, and is that if the diameter of the volume is strictly less than epsilon, structure model of one of these 7 geometries. So meaning the space is homeomorphic to a quotient of one of these 7 geometries. So instead of going through all of them, I tell you which one is not there. So hyperbolic geometry is not there. So so this is because hyperbolic spaces cannot collapse. So now here, the one thing that we haven't talked about is irreducibility. So I will mention that. So now, what is the obstruction? Is the simplicial volume to collapse is simplicial volume. So these rules have hyperbolic geometry. So this is because the simplicial volume of a collapsing Alexandrov space is 0. This was proven by Mitsushi and Yamaguchi. And then one can show that hyperbolic geometry implies non-vanishing simplicial volume. So that's the work of Thurston and Gromov. And then, well, these path, then using this, one rules out hyperbolic geometry in this statement. And this, so this statement was actually originally proven by Shioya and Yamaguchi for Riemannian manifolds. They proved an equivalent assuming prime Riemannian manifold with infinite fundamental, but one can sort of, after the proof of geometrization, one can, this is an equivalent statement. And now, what are the ideas in the proof? So, right, so Mitsushi and Yamaguchi and this, yes?
May I ask a question?
Sure, please.
If you take the suspension over a flat torus, I guess that would be an example, all right?
No, because the suspension, the torus cannot be the equator of a spherical suspension because it has infinite fundamental group. So, but yeah, I can give you. So, for example, an example would be the suspension of P2. This would be there. You can have like a, so S3 you have the hop function, right? And then that collapses, and then you have a circle action, but then that induces a circle action on the suspension of RP2. And then that will collapse to the orbit space. Does that answer your question? Yeah, I think, okay. Okay, so now the irreducibility hypothesis, so, and this topological description, then this lets you get really explicit topological descriptions of all these closed collapse Alexandrov spaces. But here the key is irreducibility. And irreducibility here means that if you have a sphere, two-sided sphere in the space, then it bounds a disk. And if you have a two-sided RP2, then it has to bound a cone over RP2. So that is the definition of irreducibility, and then that lets you get a hold on the topology, and so it restricts the topology, and then actually you have to go case by case and check that the spaces you get are actually geometric. So you can get out of the local topology, you can actually see how well I can obtain this space as a quotient, say, of the sphere or other geometric spaces. And then, well, this is a seminar on symmetries. So actually, symmetries do come into play. So going back to answer to Christoph's question. So examples of things that collapse are spaces with local circle actions, and these were classified by Jesús, Núñez-Zimbrón, and in the global circle action case, and then by both of us in the local case. And let me conclude with that. So here, as I said, basically you can always think of a non-manifold space as coming from a three manifold with an involution, and these involutions were studied by the topologists. So one also uses that to sort of understand the double branch cover that's of the spaces. And then so here the spaces with circle actions, the this enters in a key way into the proof. This is a structure theorem that says, well, that if you have any closed Alexandrov space in dimension 3 with an isometric local circle action, then it is equivariantly homomorphic to a connected sum of this form. So you have M. Here, M is actually a closed ring manifold with a local circle action. And then you have finally many copies of this example that I gave you, the suspension of RP2. For here, these copies are can be empty, right? If you don't have anything, then you're in the manifold case. But you can think of this as saying that all the singularities, all the topological singularities of such a space actually are coming from taking connected sums with suspension of RP2. And what's most important is that, well, one can read, the action has certain invariants that one can read of the orbit space, and this determines completely the homeomorphism type of these spaces. So in particular, these spaces collapse to a two-dimensional thing. So then one uses this theorem to control many of these cases. And this theorem sort of unifies work for manifolds that was done in the 60s, like Raymond for circle actions, and then later by Orlik and Raymond and Finn-Tuchel for local circle actions. Then one can put this and throw in the non-manifold case to get this statement, and then, well, this is sort of a bird's eye view of the ideas in the proof. As I said, one goes really case by case. You look at collapse to zero dimension, then Mitsubishi and Yamaguchi have a structure theorem, and then one can see that the spaces are geometric, combining them with the classification of spaces with non-negative curvature. Then you look at collapse to one dimensions, and then you again go through a list of pieces, and then you see, and collapse to two dimensions is the most involved case, and there one has to one can use this. Now the limitation of this result is that if you remember, here, there are these generalized hyperspaces. So in some cases, these spaces will have local circle actions, but there is this one case in which the fiber is an interval, and those cases are not, so you cannot consider, well, this theorem does not cover those cases, and those one has to do by hand. So this means that, well, if you have a classification of these generalized hyperspaces, then one could do that, but here it was sufficient with the irreducibility hypothesis to do it by hand. And then, well, so this is what the story is right now. So this theorem actually sort of puts together all the previous results on the topology and geometry of three-dimensional Alexandrov spaces. And let me conclude with this general question. So what else can one say about these non-manifold Alexandrov spaces and even manifold Alexandrov spaces, right? One you can think of this as asking, well, which results actually depend on having a smooth metric, and which don't. So here you can think, what else can one say about three-dimensional Alexandrov spaces? And then with this, let me stop and thank you for your attention.
Thank you for, excuse me, thank you for a beautiful talk. Very nice. Are there questions?
Hi, Fernando. This is Ravi.
Hi, Ravi.
Can I ask a quick question?
Please.
Can you go back a few slides? There was this theorem about connected sums with, or is it suspensions of RP2s? Yeah, that one.
Yes, sorry. Let me. I don't know what I did.
You just slipped by it. So.
That one.
Yeah. So
This
can
one?
you say, yeah, can you say something about the number of summands, or is it true for any number? Sorry if my question is ignorant, I know that, but.
No, actually it's actually it's a good question. You can take any, so more, let me see if I can write it here. So what the more precise statement is that you get a set of invariants. Whoops. So you get, let me erase this. I'll just say it. So what you have is, so if you have a space with an action, then what you see is that you get a set of invariants. And conversely, then you show, or well, Jesús showed that for global actions, and then also for local actions, that every given set of invariants can be realized by a space. And in particular, the number of, so what you have is, so let's see. So for example, an example of an orbit space would be something like this. So if you take, for example, this space that I said, suspension of RP2, the orbit space, if you sort of take quotient by S1, it's a 2-disk, and then what you have is these points that are marked here in red. These are fixed points, meaning they have isotropy S1 and S1, and then you have one half of the boundary has also isotropy S1, and then this other part of the boundary has isotropy Z2. But then and then, for example, if you imagine that now you can do something like an equivariant. You can take a connected sum of these spaces by, say, cutting things here, and if you have another, for example, another orbit space, so suppose you don't know what it has, maybe on the other, I don't know, something here, but if this has also, sorry, this should be, I should be taking something around here. So you can sort of see, put together from the, this would be S1, from the, out of certain orbit spaces, you can always sort of glue them together, and this corresponds to taking these like connected sums up here. So that's the, that's kind of the idea. So just, I mean, the short answer is yes, you can arbitrarily,
Okay.
you can have arbitrarily.
So without thinking about it too much and thereby revealing my ignorance, this doesn't blow up the Betty numbers or what?
I'm sorry?
Does this blow up the Betty numbers? The total Betty number.
The Betty numbers. Well,
it's okay. I mean,
yes,
if
right?
you know the answer, that's fine. I was just curious.
I mean, these are simple. Well, I guess these are simple. Yeah, I would think so. Yes, I mean, this is what is the. These are simply connected, so you have 0 and then in dimension. Well, I mean, I guess maybe you have in dimension 2, I guess. Yeah, I mean, but yeah, the topology gets like bigger and bigger. Yes, that's the. Right. So. Yeah,
okay.
I
Thanks.
To do my
As I said, sorry for my ignorance. It's just it looked interesting.
So, yeah, but thanks.
Are there other questions?
Yeah, can I ask a question?
Mm-hmm.
Is there anything you can move to dimension 4 in very special cases, say, or
with collapse or well, I mean, okay, for the there is an analog of this theorem for 4-dimensional spaces and T2 actions. That's also by Jesús, Núñez, and also a classification. But in general, I mean, what you can say from from the classification of I don't know where I put it. From the classification of positively curved spaces, where is this? Here. Yes, thank you. Sorry for going through the slides so quickly. So from this part, so you have this classification of spaces with positive curvature, which actually was also obtained independently by John Harvey and Catherine Searle. One has, the topological type of positively curved spaces in dimension 3, and then by this theorem of Perelman, this gives you the local structure of spaces in dimension 4. So they're all going to be locally, they're all either cones over a spherical space form or suspension of RP2. That's these are the spaces that give you that. But I mean, I think Yamaguchi has a paper on collapsed four-dimensional Riemannian manifolds, but then I think that's all that's known. So the dimension 4, I don't think there's, other than this result by Diego Corro and Matsume Asari and Núñez and Jesús Núñez-Zimbrón, on the analog of this one for four-dimensional spaces. There's no, not much, yeah, but I think that's all that's known in such sort of in that direction. Yeah, you can prove it. Well, I mean, for example, one could ask if you can define like a Ricci flow for this dimension 3. For, I mean, we prove geometrization using Ricci flow. Well, not using it, but one checks that all these arguments using Ricci flow go through. But really, the key observation is that is this, right? This is something that I mentioned very quickly, but that these spaces are homomorphic to smooth orbifolds. That's so then in dimension. So this goes through the smooth manifold theory, but you could ask, well, can you really do this metrically without using a smooth topology, smooth geometry and topology? So,
any other questions? If not, thank you again. And our next talk
thank
will
you.
be, oh, yeah.
Thank you very much.
Sure.